Hi everyone. Thanks for coming along today. Um, I'm David. I'm gonna talk to you about this. I'm gonna try and give an overview of this research program that we have ongoing here, based in Lisbon, with a bunch of different people. Um, and well, as you'll see, I think we've made some substantial progress in recent months, weeks, years. And I'm going to tell you about generalized harmonic gauge on compactified hyperboloidal slices. For reasons of time and not boring you with sort of all of the details through this very long story, my aim today is to give you kind of an overview of the very basic ideas of what we're doing. And then after I've given that sort of basic introduction to our plan, I'm going to just focus on these two papers, which have been driven primarily by Christian Peterson, who's a PhD student here in Lisbon, together with Shalab and Alex and myself. Okay, so let's get down to business. Um, our our aim in this long project is that we want to calculate gravitational waves at future null infinity from numerical simulations. And we want to do that sort of from first principles, from the point of view of computational physics, right? So the idea is there that we should come up with a scheme which allows us to compute gravitational waves at infinity from as emitted from compact binaries, say, and then we want that approximation scheme to converge to the continuum limit as we increase, or to the continuum as we solution as we increase resolution. And so right now, that's not what's typically done, and there are sort of the current state of the art is that we do kind of one of two things, or maybe three things, arguably. But essentially what we do is to perform numerical relativity simulations in where we have a compact spatial domain, so as depicted on these red slices, where we then impose boundary conditions on a time-like outer boundary. And then inside the computational domain, we extract an approximation to what the gravitational wave signal looks like at, say, a bunch of different finite radii, and then we try and extrapolate them out and up to future null infinity, which in this spacetime diagram is this thick back curve here marked as scri plus. Okay, so that's sort of approach one. Obviously, that doesn't satisfy this requirement of being a good first principles solution, because at some point the artificial boundary conditions that we impose on the time-like world tube at the outer boundary, they must affect what goes on in the solution, right? And we can argue about how good or bad we're modeling the correct behavior of the exterior that isn't there in the numerics, but in any case, as a matter of principle, we're not going to get that exactly right. Otherwise, if we knew how to do that, we would just solve the Einstein equations analytically, right? So it's clear that we have to do. It's clear that using these boundary conditions isn't really a good solution. So the second thing that we can do is, or that is done, is to attach to, say, a time-like world tube inside the computational domain. You could glue on null slices that come out and then compactify out on these null slices. That is called Cauchy characteristic extraction. And again, there, as a matter of principle, eventually the outer boundary from the computational domain will affect what happens. So that's also not perfect. And then a final thing that one could do is to actually communicate data between a standard Cauchy code and a characteristic code. And I think that's also a good approach, actually. But if you're a PDE analyst, it's actually hard to figure out, okay, what type of well-posedness result can I show? What type of theorem can I have that tells me that what I'm doing is good at the continuum level? Okay, so that's sort of an overview of what's done right now. And so here I'm just giving you a little wish list of things that we'd like, which are well-posedness. We'd like, which here just you can just think of meaning we want nice equations and solutions, and we'd also like something which allows us to take, all of the work that's been done in numerical relativity in recent uh, decades, right, to say treat compact binaries, and then naturally extend that to so that we can treat future null infinity. Okay, so what are the difficulties in this? Well,
David, I think there's a question.
Is there? Okay, well,
Eric?
go ahead.
Okay, yes. You don't mention gauge conditions. Don't you want to also choose gauge conditions at Spray Plus? Is that a minor issue compared to the difficulties you're facing?
No, I would say at the moment, so I would say this: if I have any gauge condition which lets me treat the system like this, that and have actually or, future null infinity included in the computational domain, then I'd be happy, right? I would just calculate things, and then in post-processing, if I have to then change gauge, say to get to Bondi gauge, I would say, okay, fine, I'll just do that in post-processing.
Okay,
so at this stage,
very good.
I don't want to say, I'm going to impose one gauge or another gauge, and I'm not married to anything. For now, what I want fundamentally is just something that allows me to compute in a way which converges in the limit of infinite resolution. Right, that will be my main requirement here. I could add extra things to the wish list, right? Like so Bondi gauge at Scry, right, would be desirable. But if I have to do it in post-processing, I'll accept it. Okay, so what's the key difficulty here? It's the obvious thing, right? That if I'm trying to represent an unbounded domain with finite number of points computationally, then there's a price to pay, right? Clearly you can't resolve all physics with just a finite number of grid points, and so the strategy, the thing that we do here is we compactify in radius. And we do so, the aim is to do so in such a way that we can resolve outgoing waves, right? And so from the point of view, if you look at, say, some local thing like coordinate light speeds, if you look at, say, outgoing radial coordinate light speeds there, one thing that you could do is just insist that the outgoing radial coordinate light speed is 0.1 or ideally just 1, so that outgoing waves just propagate with speed 1 in your local coordinates as they go out to Scry. The price that you pay for doing that is that necessarily the incoming speeds go to 0, and that means that then you won't be able to resolve incoming waves very well, right? Because they'll be horrendously blue shifted or red shifted as they come back from future null infinity. But the good news is that because we're treating asymptotically flat spacetimes, there shouldn't be any waves coming back from that place, right? So it's a price that we can pay and we can get away with it. So that's this bullet point here, that we want to compactify whilst resolving outgoing waves. And here again, I'm just trying to speak in very general terms, right? So any computational strategy, whether I was talking about treating the wave equation or any sort of hyperbolic PDE, whether it be full GR or in the perturbative setting, these considerations all basically apply in a similar way there. Okay, so by compactifying, right, that means that I'm going to have some kind of, say, aerial radial coordinate, and somewhere in my computational domain that quantity has to blow up, right? That's literally what I'm trying to do, and so I'm stuck with some quantities that necessarily blow up, and so if I've got some things that blow up, I want to somehow offset them against some kind of decay. And the decay that we have in this problem is asymptotic flatness, right? So that might be encoded. There are different approaches for how to do this, right? If you do the conformal field equations, or if you do a conformal treatment a la Anil and Alex and friends, right? Then the specific strategy for offsetting the big thing against the small thing, or the small thing against the big thing, right? That may differ, but in any case, what is always there are those ingredients, right? So we need to somehow manage that. And so here, some examples of how to do that are to use Friedrich's conformal Einstein field equations, right? And there you have a complete regularization. So everything is explicitly regular equations for regular unknowns. That's great. And similarly, as I've mentioned in the previous slide, another strategy would be to do Cauchy characteristic extraction or Cauchy characteristic matching. So the sort of the difficulty, say, in the case of doing this with the conformal field equations, is that then we don't fulfill everything on my wish list, right? So one of the things on my wish list was I want to be able to extend what works well in the strong field region straightforwardly up to future null infinity. And in the conformal field equations, then I'm forced to evolve curvature quantities, right? Which is, I mean, it's a absolutely correct and perfect solution to treating future null infinity, but then I have to go and figure out how to do binary black holes in that with that PDE system, right? So that means I can't just trivially recycle work that's already done. Okay, so our approach is to use these type of slices called hyperboloidal slices. We use compactified hyperboloidal slices. And we have our own way of trying to regularize the field equations, and I'm just going to sketch for you how that looks, and then I'll tell you about model problems and about spherical GR. Okay, so we have this very sort of simple-minded idea, which is the following. We take a quotation marks good formulation of general relativity, and in our case, that the specific choice is going to be GR in generalized harmonic gauge. And so generalized harmonic gauge comes attached to certain coordinates, and more specifically, it really comes attached with a tensor basis associated to those coordinates, right? So we introduce coordinates x mu bar. Those are taken to satisfy an inhomogeneous wave equation, and then we impose we use those to impose generalized harmonic gauge and the Einstein equations, and then that gives us a set of nonlinear hyperbolic PDEs. And then once that's done, right, then we say, okay, I don't really want to work with that choice of coordinates. Instead, I'm going to change coordinates to these compactified hyperboloidal coordinates. So that means I'm going to start with the big coordinates, the uppercase coordinates, then I'm going to switch to the lowercase coordinates. And the lowercase ones throughout the whole talk, they'll be the compactified hyperboloidal ones. Okay, and so the idea then is dead simple. It's just this. I'm given, say, if I take generalized harmonic in a first order reduction, I'm given a PDE system that looks schematically like this, where the matrices A, P bar, you can think of them as being symmetric, or else you can think that they're symmetrizable by a symmetric positive definite symmetrizer H, which I don't need to talk about in this talk. So let me suppress those details. But anyway, the key point is, I've got a first order reduction of generalized harmonic, and it's lovely because it's symmetric hyperbolic. And then I just take this equation, change coordinates in the following way. So this is actually in our work we have two different ways of changing the coordinates, but this is an example, right? This is sort of the simplest example. This is what everybody would use. Everybody doing perturbative work would use. So we say that the old time coordinate is equal to the new one plus a height function. And then the idea here is that h of r becomes something like R, so that level sets of little t, they look like something that looks like retarded time as you go out towards scry, as you go out towards future null infinity. So this is the height function approach to building hyperboloidal slices. And then the second step here is that you let the original radial coordinate be a function of a new radial coordinate which has the property that the old radial coordinate diverges at finite argument, right? So you can just think of tan, something like that, right? So this is exactly the approach that people have now been using and it's become sort of a standard approach in perturbative work, whether that be for, Reggie Wheeler-Zerilli or for the Tucholsky equation or electromagnetism, right, in a fixed background. Okay, so once we've chosen to work with the new coordinates, then there's just some sort of high school adjust the equations using the Jacobians to re-express this PDE in terms of new independent variables. And it turns out that if you've got a symmetric hyperbolic PDE and you have some additional conditions that are satisfied in our setting, then when you change independent variables like this, if it was symmetric hyperbolic before the transformation, it's still symmetric hyperbolic afterwards. So that's good news. And then the second thing that we have is that because there's something singular happening in the Jacobians that map between the two coordinates, we want to try and absorb that growth somewhere. And so in order to absorb that growth, what we do is look for all of inside the state vector U, there'll be the variables will look something like the flat metric plus a perturbation, and the perturbation has decay. And so then we multiply that perturbation by some suitable powers of R. Okay, so very, very roughly here, that's the idea, right? So, and then the hope is that the decay that's present inside the state that can be used then to offset the growth that comes from the compactification. Okay, so we could talk through. I could talk you through all of the details of that, but I thought for the purposes of this talk, it was better to just give you an overview, and so I'll tell you how that actually works for my favorite toy model. So here I've been saying to you that I need to offset the growth from the compactification with some sort of decay, and that means that whatever system I'm going to work with, I need to understand the decay that's present in that system. Okay, and so here what we've done is to come up with a model for general relativity in generalized harmonic gauge, and this is the model. It's called the good, bad, ugly F model, and it's easy. So there are several fields. They're called G, B, U, and F, and G just satisfies the wave equation, and that's why it's called good. That's nice. B is bad, and I'll explain why it's bad momentarily. U, the ugly field, satisfies this equation. And so we know how to understand the asymptotics of solutions to these equations, right? So if I choose, let me think of the simplest case, right, where I choose initial data for the Cauchy problem and choose initial data of compact support, right? Then we know that in 3+1 dimensions, solutions to the wave equation near future null infinity, they'll decay like 1 over R. Okay, so that sort of tells me, okay, how much can I rescale that field by? And it turns out that this wonderful term on the right-hand side of the ugly equation that actually suppresses some of the dynamical part of the radiation field of the ugly field. And so it turns out that solutions of an equation like this near future null infinity, they look like constant over R, right? So it's as if the radiation field has been fixed in time. And then the bad news is for the bad field, let me consider the special case where F here is 0. In that case, what happens for the bad field is that instead of decaying like near future null infinity, instead of decaying like 1 over R, it only decays like log R over R. And so consequently, if my strategy was, I'm going to take all of these fields and rescale them by 1 power of R, and then take that as my evolved variable inside my numerical setup, that is absolutely not going to work, right? Because then the evolved variable itself grows like log R, and that's bad news for the numerics. Okay, so essentially what happens in the bad field with f equals, or in the bad equation with f equals 0, is that this this source term dtg all squared, that term only decays like 1 over r squared, and that's too slow for the B field to maintain a full 1 over r decay. So instead it picks up this horrible log. But the good news is, if you play this game with the F field, the good news is that we can consider interesting case 2. And interesting case 2 is where we choose that the F field satisfies this wave equation, right? So we choose that box F is equal to a term which is like 2 over r time derivative of F, and then plus this extra piece here. And then the nice thing is that if we have this type of equation of motion for F, then the log behavior that would have appeared in B because of this term actually gets absorbed by the F field here, right? So this was work of Miguel Duarte and Edgar Gasparin and myself in Miguel's PhD. And so we sort of figured out this is a strategy for how to get rid of, or how to cure, the worst behaved behavior in this GBUF model by just choosing that F satisfies a nice wave equation. Okay, and so I told you that this is a toy model for GR. Let me explain how you should think of that as a toy model for GR and generalized harmonic gauge. The idea here is you can think of G within this analogy to GR, this G field. You should think of that as being like gravitational waves. The U fields, you can think of those as being like the metric components inside generalized harmonic, which are most closely associated with the harmonic constraints. So that's these guys, and then the bad field is sort of the single worst metric component, right? And the way that we could then try and understand this is by using the heuristic approach invented by Hormender and then used heavily in the proof of global nonlinear stability of Minkowski and harmonic gauge by Lindblad and Rodniansky. So that's sort of here the heuristic picture. So it turns out that this model essentially captures the behavior of GR and generalized harmonic gauge. So if you can understand this, you should be able to understand GR and generalized harmonic gauge as well. Obviously, in GR, on the right-hand side of these of all of the metric components, there are lots more non-linearities. So, but what we've done here is to just keep in the model, we just keep sort of the ones that are the worst. Okay, so when Christian started his PhD, what his first task was to do was to implement the GBUF model. To do that, we'd already done some work before Christian started. We'd already done a few works in spherical symmetry, and so we wanted to actually start to push with these toy models into the non-spherical setting. And so he implemented the GBUF model inside Zach Etienne and collaborators NeRPi plus code. And long story short, it works. So here are some snapshots of what the U field looks like in the time evolution. You see here, we choose some initial data, it propagates out, but interestingly, in this case, as it propagates out, it gets heavily suppressed because the U field, as I mentioned before, actually it has somehow slightly better decay. Solutions to the U equation, to the ugly equation, they have slightly better decay than solutions to the wave equation. And so here's a convergence plot from a spherical implementation of a closely related model that works too. And so we're sort of happy that that type of model can be treated. And so our next task was to try and consider a much more complicated system, namely general relativity, but we don't want to do that in full 3D first. And so the paper that we put out last week is this one where we consider GR in spherical symmetry. Okay, so the story here is that if you introduce suitable null vectors, so sigma here is an outgoing null vector, and sigma bar is an incoming null vector. You can check for the specific definitions of exactly what they are in the paper, but essentially here in Minkowski, sigma would just be dt plus dr, sigma bar would just be dt minus dr, and then this is sort of the sigma and sigma bar are sort of the natural curved space generalizations of that. So it's the coordinate light speed appears, and then they're renormalized by a certain scalar function. And the reason why we choose the scalar function to renormalize them is because when you make, in quotation marks, the right normalization, that's what makes the Einstein equations appear at their most pretty, right? So this is literally all of the field equations of general relativity in spherical symmetry, expressed, I mean, without suppressing any details, right? Okay, there are some shorthands here, but I think the message is clear, right? That because there's something special about null directions, if you decompose against carefully chosen null vectors, the field equations actually simplify a lot, and this is sort of the best that we could do. Okay, so this is what the Einstein's equations look like in spherical symmetry in that language before you actually impose generalized harmonic gauge, and then we impose generalized harmonic gauge, and amazingly they still don't look terrible. Okay, here let me just tell you the sort of the meaning of the variables if we refer back to the GBUF model. Okay, so C plus, that's one of the U variables. So this is one which should have better decay than a solution to the wave equation. The Fs here, they're the Fs from the GBUF model. They're the gauge source functions that we have from the generalized harmonic formulation. Okay, the T sigma sigma, T sigma bar, all of the T's here, they're just the stress energy tensor. And so C plus, and yeah, sorry, I forgot to say. So C plus is the outgoing radial coordinate light speed in our original coordinates. C minus is the incoming coordinate light speed in our original coordinates, and C minus is the one which is bad. The reason why it's bad is because if we come over here, even in spherical symmetry, if I consider that my matter content is say a massless scalar field, then the incoming null component of the stress energy tensor, that's the one that decays the slowest. And just like in the model above, it only decays like 1 over r squared. So that means this piece only decays slowly, right? So morally, the way to read this equation, these equations is there's like an outgoing derivative and an incoming derivative, right? So that's like a box operator, a two-dimensional box operator equals some sources. And then in this equation, there's an incoming and an outgoing null derivative. And then on the right-hand side, there are sources which only decay slowly, right? And so this sort of the idea of using the GBUF model then is that here this F can be used to cancel off the bad behavior coming from this. Anil, yeah, you have a question.
So is this somewhat related to the Newman-Penrose equations, but you're writing it in different variables because of the null directions?
Yeah, so surely there is a relationship, but Newman-Penrose is again quite different because Newman-Penrose goes deeper in derivatives, right? So Newman-Penrose closes the system again by introducing curvature quantities, and we're not doing that. We're closing it at the level of the number of derivatives is only the connection, right? So we're only 2 derivatives deep in the metric, whereas Newman-Penrose is 3 derivatives deep.
Okay, so you're writing essentially the Einstein equations without curvature terms along null directions with respect to this other frame.
Yeah,
Right.
exactly. I mean, but and another difference is that in Newman-Penrose, you would always take the ingoing and outgoing legs of the null tetrad. You'd normalize them so the dot product was like -2. We don't have that here, right? Because yeah. So surely there's a relationship, but it's not exactly the same. Okay, so if you like, these variable in spherical symmetry, these two variables, C plus and C minus, they sort of determine the local causal structure, right? Because they tell me about radial light speeds. And then the variables delta and r-circ. R-circ is just the areal radius. And delta is related to the determinant of the two metric that lives in the TR plane. Okay, and okay. This one isn't as pretty as the others, but it still fits on one slide, so I'm pleased. Here I should say that MMS is the Misner-Sharp mass, right, which is like the measure of mass in spherical symmetry in GR. Okay, so we're still happy with this, and then what we do is to take these equations and push them through the procedure that I described before, right? So here, there are lots of shorthands being employed here, right? Because this thing where I write d sigma bar, that really means the directional derivative along this incoming null vector, and that needs to be expanded out in terms of t's and r's, right? With big T's and big R's. And then what we do is take these equations, introduce a first order reduction, rescale variables according to the expected decay that we have from the asymptotic analysis as presented before for the GBUF model. And then change coordinates to the hyperboloidal slices. And we can change coordinates to hyperboloidal slices in one of two ways. So we either use the height function approach, which I showed you explicitly before, or else we solve dynamically the iconal equation. The iconal equation turns out to be, you can rewrite it as a nonlinear transport equation. So we solve that alongside the rest of the PDE system in order to map correctly from one set of coordinates to the other. Anil.
Sorry, I think we talked about this at some point before, maybe per email, but this MMS, so does that depend on time?
Yeah, it does. Yeah. So it's functionally it looks something like 1/2 times r-circ, open big brackets, and then it's something like GAB nabla A r-circ nabla B r-circ minus some constant. Close bracket. So it involves first derivatives of the areal radius contracted with the metric and then with some normalization factor.
Okay. So it's a dynamical quantity that's in the like a
Exactly. Yeah.
shorthand.
Exactly. So this is another shorthand. I'm just not giving you the definition on the slide. Again, it's in the paper, but this is, this is so. I mean, if you want to sort of understand intuitively at least part of the intuition behind this, it's that if you take a limit of this quantity towards spatial infinity, it's just the ADM mass, and if you take a limit towards null infinity, it's just the body mass.
Thank you.
Shut up.
Hi, David. Just a naive question. So, is this, I mean, some specific reason that why Misner-Sharp mass comes only in the delta equations, not in like
Sorry, only in which equations?
only in the delta equation?
Well, no, I mean, yeah, there is a special reason we chose to write it that way. If you've got you could also replace it inside here, right? It's just because if you look at the equation of delta, I don't have a deep insight as to why, but exactly the this combination of the Misner-Sharp mass turns up, and it's just shorter to write it this way than to write it any other way. But any equation where you've got sort of products of first derivatives of the areal radius that look like incoming derivative of r-circ times outgoing derivative of r-circ, you could always express those in terms of re-express those in terms of the Misner-Sharp mass in a clean way. This just, I don't know, we just thought that it was pretty. I guess that's the answer.
Thanks.
But I don't have a deep insight as to exactly why it's only appears there. Okay, so after a lot of blood, sweat, and tears, this is implemented. And now I'm going to tell you, I'll walk you through the numerical results. So in the paper that we put out last Friday, we presented a sort of what I think is quite a comprehensive suite of numerical work with spherical general relativity. Basic dynamics look a bit like this. Let's see if I can play this again. I think it might be a bit laggy on the Zoom connection. So let me just explain what happens. So we start with constraint violating initial data, and that's a good test to, what we started with constraint violating initial data, and that's a good test to start with because if I have sort of constraint violations and scalar field, then that will definitely agitate gauge perturbations as well. And so that means that by choosing this type of initial data that violates the constraints, it's kind of like I'm exciting every part of the PDE system in a very hand waving sense, right? So it's a good test to find out, you know, if like does this numerical implementation of this PDE system have any hope of actually working? And the answer is, well, if we look at scry, so here's future nil infinity, the reflections are essentially negligible by I, and if we have small data posed as the initial data, then it disperses, and it leaves it sort of leaves the computational domain, and then there's some stuff left behind which very slowly decays. You might ask yourself, okay, we did all of this heuristic work to try and understand understand decay of fields. Was that right? Was that wrong? Well, if you don't use the gauge driver, if you don't use that special choice of equation of motion for the F field, then the variables just explode in the time evolution, but as soon as we turn on the gauge driver, then we get this nice behavior where everything seems to decay well. So that's evidence that the heuristics are indeed telling us something useful, which is good to know. And we've also worked out how to solve the constraints within this formalism. So that was Shalab's big victory. So we have constraint solved data too, and we can evolve in data either with a regular center, or we can evolve data which is, say, a black hole or a perturbation of a black hole with scalar field perturbations. So we're happy with our initial data. There are some limitations at the moment in the choices of initial data, but Shalab promises me that he can overcome them. So that's good to know. So that's something to look forward to in the future. If we look at norm convergence, so here we're not trying to do high order, right? We're not trying to do even fourth order or spectral, nothing like that. This is just a simple finite differencing setup, but nevertheless, the convergence is convincing. So we get good, I think, very nice, clean second order convergence also for long evolutions. And that works whether we're treating spacetimes with a regular center, or if we're treating say perturbations of Schwarzschild. We get similar results whether we're using the height function to build the hyperboloids, or if we use the iconal Jacobians. So Anil wisely asked us if we could give an argument to say that one is better or worse, but in the time evolutions, really the answer to that question is that they seem to be very comparable. It's a little bit more of a pain to construct initial data with the height function, but then on the other hand, you have to evolve more PDEs if you're doing things the iconal way. So swings and roundabouts. We can evolve initial data so if we ramp up the size of the scalar field, then we can evolve initial data which collapse to form a black hole. And so here, if I move my zoom bar out of the way, so here are a set of snapshots from a run in which an apparent horizon forms. And I think here Christian took these snapshots just after the apparent horizon had formed. Nevertheless, the method continues to evolve later. So this is the initial data. It evolves a bit. An apparent horizon forms, and then we start excising. And here, what we're doing is setting the fields to 0 inside the apparent horizon as a visual aid. So you can see that the apparent horizon is around here. Similarly, we see if we look at, say, Bondi mass loss, right? You'd expect that as scalar field leaves the space-time through future null infinity, then the Bondi mass should come down, and indeed that's what we see. So if we start with constraint solved initial data, then we see that, okay, at early times nothing happens. This is before the scalar field actually hits future null infinity. But as soon as there's a non-trivial flux of the scalar field onto scry, then the Bondi mass starts to decrease and asymptotes to 0. So we're very happy with this. We have also looked at small perturbations of Schwarzschild, and when we do that, then we see, we can get something reasonable regarding quasi-normal modes, and then at later times something reasonable regarding tail decay. Here we didn't really try and push digits, right? We haven't tried to do things very, very accurately. This is more sort of proof of principle. So I guess that by tuning the initial data and by ramping up the resolution, I hope that we'll be able to do something a little bit better than this. But nevertheless, this serves as a nice proof of principle that we're capturing in the linear regime. We're capturing all of the physics in the right way, as you'd expect. And so essentially, this is sort of the roundup of what I think one can do in spherical GR. There are a few things left over, so we could try and treat very extreme spherical spacetime. So we didn't make, so here, for instance, we've done collapse, right? But we haven't made any effort to tune to the threshold of collapse. But for now, I think that's a separate problem, because the gauges that we're using here, everything is sort of tailored towards getting future null infinity to work, and then we'd have to work a bit to make things sort of interpolate between the good gauges for critical collapse and the good gauges for future null infinity. Anil.
So I want to mention here, I guess maybe you're too humble to say, but as far as I know, I haven't seen any kind of hyperboloidal evolution that can do the tail like this. So, there are other hyperboloidal evolutions, like Oliver Rinne has done some, Luisa has done some, and so on in the past. But I don't know if anybody has done the tail at scry with nonlinear evolution with hyperboloidal code.
I think Alex may have.
Okay.
Yeah, he's nodding.
Yes,
Alex.
looks pretty similar to this. What if I comment on a little detail here is that, well, I mean, that was tested a long time ago. I have not reviewed this yet in the conformal compactification approach that I am following, but it's a bit of it's something I want to review, because while the scalar field is propagating non-linearly with the black hole, there was also some dynamics in the gauge for the black hole. So I would like to understand that better. But yeah, I did get some similar plots to these, although again, I did not study that in detail.
Yeah, so anyway, Anil, I'm very happy with this result, of course. I think it's really nice. And I think there was another question as well. I saw 2 raised hands, but no. Oh, I see. It was
Sorry.
Yeah.
I just wanted to ask, you don't use any boundary conditions at scry? I mean,
No.
How do you evaluate the field?
No, because so it's a good question. So of course, if I just pick a say some hyperbolic gauge condition, right, at random, then what you'd think is, okay, then you are going to need to pose boundary conditions at scry. But one of the strengths of doing generalized harmonic is that everything is the speed of light, and scry is incoming null in the domain. So that means no boundary conditions are needed. So in fact, what
No,
we
I understand that scry is a special
so
location, but you
yeah,
know,
so
when you have formal singularities in your equations, when you have matter field, there.
so
I
yeah,
mean, if
so
it is massless, it's easier, but yeah.
so yeah, good question. So for in the massless field, there are no formally singular terms whatsoever. And if you look at the way that our equations turn out, the formally singular terms only appear inside the fields which I called the U fields. So there's one formally singular term in one of the C plus reduction equations of motion, and there's one formally singular term in one of the epsilon reduction variable equations of motion. But those are the variables that have sort of frozen asymptotics at scry, actually. So maybe I can even show you that if we go back to this. So if you look, say, in this plot, right, some of these fields, they go to zero at scry throughout the entire evolution. Those are the ones actually with the formally singular terms. So it's sort of in our setup, like the formally singular terms actually, they're forcing the solution to stay zero, and then and it does, right, and it still looks smooth. Whereas these ones which shift away from zero, like the green curve here, which variable is that, delta, and C minus, those don't have formally singular terms. They seem to be well behaved. And then again, so for the reason I said before, from the like in the code, because we don't need to specify continuum boundary conditions, what we do for the actual treatment of the boundary is, for the treatment of scry is, we treat it in exactly the same way as we treat the excision boundary at the black hole. So we just extrapolate and then use centered finite differences everywhere. And then for the terms with formally singular, or for the equations with formally singular terms, then we just apply L'Hopital. That seems to be sufficient.
Yeah, that's what I expected.
Does that answer your question?
Okay, thanks.
Yeah. Thanks. So here, and I think that strategy would also generalize, right, to higher order methods. And in a way, it's also it's essentially the same thing that Oliver Rinner does, right, in his constrained evolution setup. Right, he also L'Hopital's things. Okay, so let me conclude. So our motivation is to calculate gravitational waves at future null infinity, and for that we're developing a method for numerical relativity that employs compactified hyperboloidal slices. We're using this formalism that we came up with called the dual-foliation formalism. And an interesting thing about our setup is that we actually sort of have to look at the specific form of the nonlinearities of GR, and I think that's really interesting that it's needed to, you have to look at that in order to make the numerics work, right? The fact that there's one Einstein equation that has worse decay than the others, and that one equation has to be that behavior is worse because of the form of the nonlinearities, and then that equation has to be treated a bit more carefully. I think that's very interesting. We are using a careful choice of gauge to suppress these horrible log terms that we don't like, and hot off the press from last Friday is that now we're confident that spherical general relativity is under control. And so our next mission we're moving on to is to do 3D GR without symmetry. Thanks for your attention.
Thanks,
And
David.
I'm here for questions.
Okay. Before I stop the recording, I should correct myself. I see that Moncrief and Rinne have already also calculated tails with matter fields. So I forgot about that paper. I just found.
Okay.